Welcome back to my channel. This is Meghana from Sri Venkateshwara College of Engineering. Today I am discussing about DMS in that topic fundamental principles and counting. First we'll see about the fundamental principles of counting. Counting is a fundamental concept in mathematics. It is essential for understanding the size of sets, this relationship between quantities and the probability of the events. Next, the multiplication principles. Decision points. Imagine a task with a series of independent choice. Second one, independent outcomes. The total number of possible outcomes is found by multiplying the number of choice at the each step. Example, a restaurant offers 3 appreciates, 5 main courses and 2 desserts. There are 3 into 5 into 2, we can see here 3 into 2, 5 into 2 is equals to 30 possible meals will take. Permutations. Definition, formula. In this we'll see about definition, formula and applications. First, definition. A permutation is an argument of objects in a specific order. For example, the permutations of the letters are A, B, C. In that we'll have the possible values are ABC, ACB, BAC, CBCA, CAB and CBA. That formula is the number of permutations of n distinct objects taken are at the time of denoted by NPR, or is calculated as NPR is equals to n factorial by n minus r whole of factorial. Applications. Permutations are used in a variety of fields including probability, statistics and computer science. They are also used in cryptography and code theory. Next we'll see about combinations. Combinations are unordered selections of objects from a set. The order of selections does not matter. Formula, in the backslide we saw the formula NCR is equals to n factorial divided by r factorial into n minus r factorial. Example, choosing 3 students for a class of 10. Application, probability, statistics, coding as same before slide. Next we'll see about the pigeonhole principle. Pigeon principle. A simple idea. If you have more pigeons then pigeonhole that at least one pigeonhole must contain more than one pigeon. Powerful tool used to prove existence of something without explicitly finding it. Wide applications, continuing combinations and other arrays of math. The pigeonhole is a fundamental concept in mathematics that has far-reaching applications. It is simple idea but it can be used to prove powerful results. The principle states that if you have more times than counters, then at least one counter must have more than one item. Next we'll see about the binomial coefficients. Mathematical representation. Binomial coefficient denotes as n choose k or nck, represented by the number of ways to choose k items from a set of n distinct items without regard to order. Combinational formulas. The formula of calculating binomial coefficients in nck is equals to factorial n factorial divided by k factorial into n minus k factorial, where n represents the factorial of n. Applications in probability. Binomial coefficient plays a circular role in probability, particularly in calculating the probability of events involving multiple trials without two possible outcomes. Next we'll see inclusion exclusion principles. Overlapping set. The inclusion exclusion principles helps us contain the elements in union sets with those sets overlap. Connecting with care. We hide the size of all individual sets, then subtract the size of their previous insertions and so on. Alternating signs. The signs are alternate for each level of insertion, ensuring each count elements exactly once. Next we'll see about generating functions. Generating functions, mathematical tool to represent sequence. Coefficient of x and k represents the kth term of the sequence. Operations of generating functions correspond to operates on sequence. Solving combinational problems by multiplying generating functions. Generating functions are powerful tool in combinations, allows us to represent sequence as polynomials or power series. The coefficient of x and k in the generating function corresponds to the kth term of the sequence. This connection allows us to multiply generating functions to solve combinational problems. Operators on generating functions such as addition, multiplication, differentiation considered to operation sequence, such as adding items, multiplying terms and taking differences. Next we'll see about the reference relations. Recurrence relations are powerful tools of defining sequence of pattern. Base case, initial value for the sequence. Recursive step, define terms in the sequence in items of previous item. Solving, find the explicit formula of the sequence. They are particularly useful in analyzing algorithms where they can be used to modify the time complexity of a recursive algorithm. Example of recursive relation including the Fibonacci series, where each term is in the sum of the two preceding terms. Next, counting techniques in probability. Probability fundamentals. Probability theory is built up the foundation of counting techniques. We rely on counting the determined and likelihood of every events occurring. Counting simple space. A counting technique or circular of calculating the size of simple space, where is the set of all possible outcome of the experiment. Calculating probabilities. By understanding how many outcomes satisfy a particular event, we can compute the probability of event happening. Real world applications. Counting techniques are virtual of analyzing data, preceding outcomes and making informed decision in various fields. This is about today's. Thank you so much.